Thank you for joining the talk, and I would like to introduce today's speaker. Our speaker today is Mr. Shantanu Lanke. He is a graduate student at Arizona State University, and his work is related to the aberration correction for the transmission electron microscopy. I must mention that ASU is a global leader in high-resolution electron transmission microscopy and offers cutting-edge labs equipped with advanced electron microscopes to probe the physical, chemical, and electronic structure of matter at atomic scale. And the main purpose of today's talk is to incite some interest and highlight the importance of aberration correction for electron microscopy. The main talk would be around 45 minutes, and then we will proceed towards the question answer session. Everyone is welcome to post their questions in the chat, and we will try to answer as many as possible at the end of the session. So you also have the email address of the speaker in the chat, so you can also email him. So now I would like to pass on the mic to the Mr. Shantanu.
Yeah, hello. Thank you very much for the introduction. So just let me start. So yeah, so my screen is visible to all of you. Okay, I hope, yeah, it is visible. So today I'm going to talk about the journey towards aberration-corrected electron microscopy, like how aberration correctors were developed. And it really took a lot of time, a lot of years to build first working aberration corrected or successful aberration corrected electron microscope in 1998. So here on my first slide, you can see this small piece of hexapole corrector element here. So you can see it's non-rotationally symmetric, and you can see the multiple components here, which was used in the very first aberration corrected microscope. So why I selected this topic? Because this topic is very interesting, because it took significant time for the people to work on the aberration correction. And here is actually the time from when the first electron microscope was invented by Ernst Ruska, and when the first aberration-corrected electron microscope came in reality. The time was actually more than when the Wright brothers invented the motorized manned aircraft and the moment when the first man put the foot on the moon. So that's why it's very interesting to talk about like how the journey of this aberration correction went. And here, so first it was Ruska who invented the first transmission electron microscope. And at that time, he was unaware of the wave-particle duality, because unlike today's days, we didn't have so much resources like internet and etc. So he was totally unaware of the wave-particle duality, and while he was working with cathode ray oscilloscope, he just invented the transmission electron microscope. But the resolution of the first TM was no better than the light microscope. Then Ardina, just followed by the invention of conventional TM, Ardina in 1938 invented this STEM, scanning transmission electron microscope. And at that time, it wasn't really good because we didn't have the high brightness tip as the electron source, and we had the clumsy recording system. So it wasn't very efficient at that time. And then the biological electron microscopy flourished in 40s, and people started using transmission electron microscopes for analyzing the biological samples. Then the Peter Hirsch in 50s, he thought of using the electron microscope, the TM, for characterizing materials. So here you can see this is the aluminum thin foil, and it's having the dislocations here. You can see these dark lines here. So it was first the beginning of the application of TM in materials field was started by Peter Hirsch in the 50s. And then as the microscopy improved in 60s, people started chasing the lattice fringes. So at that time, we didn't have the aberration correctors, but we still had the atomic resolution images without aberration correction. And here the resolution is good, but the resolution is about 2 angstroms and not excellent, not sub-angstrom resolution like today's days we have. And then here in the 70s by Sumio Iijima, who imaged the first titanium niobium block oxide. And here you can see the atomic resolution image of this oxide material here. And you can see these white spots here. They are just the tunnels between the atomic columns, and the dark spots here, they represent the atoms of metals like titanium and niobium. We don't have oxygen here. We cannot see the oxygen. And here, if we increase the voltage, we know that if we increase the accelerating voltage, we reduce the wavelength of the electron microscope, and somehow we get a little improvement or enhancement in the resolution. So here, Basil and Smith in 80s, they imaged this tungsten oxide showing this crystallographic shear plane. And here you have pentagonal bipyramidal defect. And these black spots you can see here, they are the metal atoms of tungsten atoms. Then, how can we improve the resolution? So there were a lot of effortless attempts to develop aberration correctors, but most of them had failed. And so people came out with the process of increasing the accelerating voltage. So the accelerating voltage is increased. So they were thinking about mega electron volt electron microscopy. So here, the resolution, here I'm talking of Scherzer resolution or structure image resolution or directly interpretable resolution. So for conventional TM, which is parallel beam TM, it's this, and for STEM, it's actually 0.43. So by mistake, I just forgot to correct it. So it's 0.43 CS lambda to the cube raised to 1/4. So, and obviously we can see from these equations that we have a better resolution in the STEM mode. So one way is to decrease the wavelength by increasing the accelerating voltage, and the other way is to reduce this spherical aberration coefficient. So CS, it's basically third order spherical aberration coefficient. And so in the 80s and 90s, so this is the instrument. So the Hitachi and JOL developed this mega electron volt electron microscope. So you have the accelerator component on the top of it and your imaging here. And this significantly improved. So the target at that time was the 1 angstrom structural image resolution. So when we employ this microscope, then we just got 1 angstrom resolution. Here you can see this is the optical diffractogram of amorphous germanium. And this diffractogram is recorded at Scherzer defocus. And you can see that we have just achieved 1 angstrom resolution. And this is the contrast transfer function of the experimental result, and this is the simulation. And you just, here is your first 0 to nearly 10 per nanometer, and you just got 1 angstrom resolution. And then Tonomura in 2000, they imaged the gold thin films at 1 mega electron volt transmission electron microscope in Japan. So here you just got the 0.5 angstrom of lattice fringe resolution. So this lattice fringe resolution is different from the structure image resolution here. So you can see the lattice resolution is twice as good as the structure image resolution. And here you can resolve these 0.498 angstrom lattice fringes of gold. And then this was about parallel beam TM. And what about STEM? So at STEM, we had a lot of problems at that time, like stability of the microscope, and you should reduce the noise, environmental noise. But still, people were able to image the individual atoms of high Z elements like uranium or thorium. So this image shows the thorium atoms on the amorphous carbon support. And this was still possible because there was, at that time, the field emission gun, so which has very low energy spread, and the field emission gun gives you better resolution as compared to thermionic emission gun. And this image is recorded at 30 kV STEM in 70s. So then John Colley, so from ASU, he came with the reciprocity theorem. So, and the reciprocity theorem basically tells that if you have TM, and if here you have electron source and here you have detector, so you can just flip these two components here. So you can bring the electron source here and then you can have detector here. So the STEM is just the same thing as you make conventional TM upside down. So this is what reciprocity theorem means. So in this way here, you have broad beam TM, and in this way you have STEM. So then in STEM, you can see here, this is the optical transfer function for STEM, and this is the phase contrast transfer function for conventional TM. And you can see here, there is the first 0, it's just before 0.5 per nanometer. And you have, so if you take the reciprocal of this point here, then you get the structure image resolution, or you can call it as Scherzer resolution. And from these transfer functions, it's very clear that which one gives you the better resolution. So it's the resolution obtained for STEM is obviously much better than the one obtained in conventional TM. So then, so why we need aberration correction? Because we are using high voltage electron microscopes, but there are a lot of problems with high voltage electron microscopes. Like you have, main problem is the radiation damage. So you're using extremely energetic beam, and that energetic beam can probably damage your sample significantly. And that can lead to some artifacts, or you can see that can compromise the resolution, and that's not desired. Another problem is the stability of the electric components, the electromagnetic components. You are working at very high voltage, so stability of the electric component is important. And another thing is you have insignificant chromatic aberration at high voltages, but you increase at the high voltages, the spherical aberration becomes dominant, because there is no direct relation of CS to the energy, but the logic behind that is when you increase the energy of the electrons, so at the same objective lens excitation, the focal length of the objective lens increases with increasing the electron energy. And that leads to the increased value of CS, because the CS is proportional to the focal length of the objective lens. So the Scherzer theorem says, CS, or the spherical aberration, is the fundamental lens defect, which is intrinsic to any rotationally symmetric lens. So no matter what kind of lens I have, what kind of pole pieces I have, what shape of my pole pieces have, and regardless of that, I'm going to have this CS in that rotationally symmetric lens. So, and Scherzer only suggested 3 possible solutions. So because we have the constant field excitation of the objective lens, so he suggested maybe we can use the time varying fields, or maybe we can use electron mirrors, and we can use non-rotational fields. So these first 2 approaches became popular at the beginning, but none of them gave any useful information or the success. But then the people thought of non-rotational fields. So maybe we can use multiple lenses like hexapole or quadrupole, octopole. And people tried working with the multiple lenses, but in that, so multiple lenses have their own aberrations. So means you're destroying the evil, but in return, you're also giving rise to another evil. So at that time, we don't have like the mechanical alignment systems, and people were not able to precisely align those multiple lenses in the microscope. And again, a lot of these approaches gave nothing. So they all were failed. And the funding agencies were just tired. So they just said, like, we are not going to fund you anymore if you're talking about aberration correction. But then people were also working on offline approaches, like, so you can use software to correct the aberrations. So the first approach is focal series reconstruction. So here you record the images, high resolution images at different defocus, and then you just reconstruct those images and you correct the spherical aberration thereof. And another way is off-axis electron holography, so which is also indirect approach, and this can also be used to correct spherical aberration and astigmatism in the images. And the another is online or direct aberration correction. So there are again 2 things: image correction. So image correction is performed in conventional TM, and the probe correction is performed in STEM, or scanning transmission electron microscope. Then here you have focal series reconstruction image of, this is YBCO, which is high temperature superconductor. And this image was a reconstruction of 124 different defocus values. So after reconstruction, you are finally able to see this oxygen atoms in the vicinity of heavy metal atoms. So this is the first time people were able to resolve the low Z elements like oxygen with software or indirect based aberration correction. And then this is again LiCOO2, which is the lithium battery material. And here you can see this faint blobs, faint white blobs, they correspond to lithium atom. And it's the first image of electron microscope where the people had recorded the lithium atoms. It was the first time when people were seeing the lithium atoms in the vicinity of heavy cobalt atoms. But still, the difficulty is to see the oxygen atoms. You cannot see the oxygen atoms very clearly, but here there are some oxygen atoms you can see. And in this image, it's quite difficult to locate the oxygen atoms and also lithium atoms. And here, so the application of electron holography. So basically it's off-axis electron holography. So in that you record the hologram, and then when you Fourier transform it, then you observe this sideband, and you just apply a numerical phase plate, which is just the inverse of the coherent aberration function. And when you apply this numerical phase plate to this sideband, then again you perform inverse Fourier transform to get a complex wave function. So the complex wave function has two parts, one real part and imaginary part. So real part gives you the amplitude contrast and imaginary part gives you the phase contrast. So here you can see this is the amplitude contrast and this is the phase contrast. And here you can see the silicon dumbbells. So this was the first time when people made use of off-axis electron holography, and they were able to observe the silicon dumbbells for the first time. And now let's move to the CS correction. So here, like light optics, we have a lens, and because the rays which are making higher angles with respect to the optic axis, they are bent very sharply, and so they are just not converging at the same point. So for this rays here, so you have different focal point. For these rays, you have different focal point, and so on. So generally with this spherical aberration coefficient, you usually record the image at this point here, which is often called as a disk of least confusion. And there is a way to correct these aberrations in light optics by just employing a diverging lens here. So when you are employing the diverging lens, so what basically we mean by a correction? So basically we're imposing a negative spherical aberration coefficient to the objective lens, and thereby we are correcting for the positive spherical aberration of our objective lens of interest. And there how you get the spherical aberration corrected. So, but in reality, the similar approach should be there in terms of electron microscopy or electron optics. But unfortunately, the electron optics work on the base of magnetic lenses and from Gauss. So where I was, so we don't have any concave lenses or diverging lens for electron microscope. So if you have a rotationally symmetric lens or round lens, it's going to always converge the electron beam. So you're going to end up with always having positive CS value, and we have to compensate that. So somehow we have to compensate the CS with the negative spherical aberration coefficient. And then after all attempts were failed, no one was ready to fund for aberration correction. But these three superheroes in aberration correction, they just managed to get funding from Volkswagen Foundation project. And it continued from 1991 to 1997 because the alignment, the mechanical alignment and electrical stability of the lens components was very difficult to achieve. And after doing that, in 1998, they came up with the first aberration-corrected electron microscope. And it was image-corrected electron microscope. So the principle of this hexapole lenses, so they used a double hexapole lens. So what you have, basically you have the hexapole. So the plus minus sign just correspond to north or south poles. And this is the central tube through which the electron beam passes. And because of a rotational asymmetry, you end up with getting a distorted beam. So when your circular beam passes through this hexapole, you're going to get a triangular beam. And that's what I was trying to tell you, like we are introducing extra aberrations. So here we have introduced 3-4 astigmatism. And so how to correct that? So then you have another hexapole with the poles rotated by 60 degrees or the alternating pole. So here you have minus, here you have plus, here you have plus, here you have minus. So then that triangular beam is again passes through this second hexapole, and there it gets again circular. It's again attains circular symmetry, and but at this time you have a diverged beam, so the beam divergence takes place. So you have so this combined lens is basically the diverging lens of Rosa, which was proposed in 1990. And this was the first aberration-corrected electron microscope of Max Heider and Knut Urban. So in 1998, so this microscope is Philips CM200. So it's a 200 kilo electron volt microscope. And here you can see the circled component here. It's the image corrector made up of double hexapole lens system. And even if it sounds simple in theory, in reality, it's actually difficult. So the beam path is really complicated. So here you have objective lens, here you have transfer doublet, here you have first hexapole and second hexapole. And at that time, they imaged the gallium arsenide sample. So the resolution was not very high in the first aberration-corrected electron microscope, but the resolution was 1.2 angstroms, and the atomic spacing between this gallium and arsenic is 1.4 angstroms. So you can see that you can easily resolve this 1.4 angstrom atomic spacing. And I have just a small video here to show you. Do we need these aberrations? So why can't we make the aberrations zero? We can bring the aberrations down to zero. So this is delta F, so which is defocus value. So that we can control easily by changing the objective lens excitation. We can make it zero, we can make it positive, we can make it negative, or over focus or under focus respectively. And now we are able to correct for CS2. So is it worth or is it wise to make the CS and delta F zero? So if you make this CS and delta F zero, so basically in your contrast transfer function, you plot this aberration function chi of k, you plot this sine chi of k versus k. K is the special frequency in the reciprocal space, and you just plot that, and that is your phase contrast transfer function. So if you make these terms here zero, then you're going to end up with no contrast. You have contrast transfer function drop to zero. So any one of these, if you make zero, so you're going to end up with no phase contrast information. So here I'd like to show you a small video. I just picked from this website here, and here you can see. So this is a lithium dendrite. So I'm magnifying, it's melting in conventional TM. And in cryo-EM, it doesn't melt when you zoom out, but it's not for what I'm showing in the video. And the end of the lecture, you just attend these ages. So this image is recorded with under focus. So when you arrive at delta F of zero, then you just lose the contrast, you can see. So there's almost no contrast there as you approach to defocus value of zero. So we need these aberrations because they are encoded with the phase information. And if I'm doing the phase contrast imaging, I need these aberrations. So I have to tune those aberrations. Then this is, so I can make the CS, I can make it positive, I can make it zero, I can make it negative. So what if I make it negative? So if I'm making this CS value negative called NCSI imaging, which is negative CS imaging. So here this is strontium titanate at 110 projection. And in generally, if you record annular dark field image of strontium titanate, you won't be able to observe this low Z elements or low Z atoms like oxygen. But in NCSI, here you can clearly see the oxygen atoms are visible. It was the first time the oxygen atoms were imaged by using NCSI technique. And the application of that is, especially in situ transmission electron microscopy, the people who are working with catalysis, they often deal with water splitting reactions and carbon sequestration, conversion of CO2 into fuels, and which involves low Z elements, including oxygen, hydrogen, or if you're imaging some boron nitride or some gallium nitride stuff, then you have to locate the low Z elements. And in that case, this NCSI imaging was very useful. So basically, when we have positive CS and a negative focus, that is under focus, then basically you have dark phase contrast and bright amplitude contrast. So they both cancel each other and you lose contrast there. So in NCSI, these non-linear image contributions, they just enhance your contrast and you result in observing these low Z elements close to these high Z elements like strontium and titanium. So after this achievement in 1998, Andre Crevanek came with aberration corrector for STEM. So his corrector was a bit different from the hexapole corrector. His corrector involved quadrupole and octupole lenses. So basically what you do, you have quadrupole. So you're getting an ellipsoidal beam when it passes through the quadrupole. Then you correct the spherical aberration in that direction after bypassing it through the octupole. And then you again pass it through quadrupole to make it again round beam. And then you pass it through another octupole to correct for fourfold astigmatism. And again, you pass it through quadrupole to make it ellipsoidal in orthogonal direction as compared to the previous one. And then you correct C3 in that direction by using another octupole. And then again, you recover the shape by passing it through another quadrupole. So basically you have 4 quadrupole and 3 octupole lenses. So this is the basic principle. And when they imaged with this type of corrector, so this is the probe corrector. So it's used for STEM. And here you can see a small gold island here on the amorphous carbon. And you can still see that you have an atomic resolution here. You can see the gold atoms. And then in STEM, you have different modes. So you have ABF mode, which is annular bright field image. So basically you have an annular detector, and in high angle annular dark field image, your contrast is proportional to Z to the square. It's not exactly Z to the square, but it's Z to the 1.6 to 1.7 or 1.8. But let's approximate it to Z square. But in annular bright field, this contrast is about Z to the 1.2 to 1.4. And because you have circular detector with the hole in the center, it's a ring-like detector. And the most of the electrons, they just pass through that central hole in the annular bright field mode. And you just record this image of the light elements or low Z elements into this by using ABF detector here. And for high Z elements, most of the electrons scattered through high angles, and they are just detected on ADF detector. And here again, you can see, you can locate these oxygen atoms here. So you have these oxygen atoms in strontium titanate, in TiO2. You can still see this is a HADF image. And in HADF, you don't see actually the oxygen atoms, but in ABF, we're able to resolve these oxygen atoms clearly. And here is LiV2O4. And here also you can clearly see the oxygen atoms. And this is another example of yttrium hydride. Now it's hydrogen, so Z is equal to 1. So now you're seeing the hydrogen atom with ABF stem, which otherwise is just invisible in HADF mode. So in ABF, you can clearly see this hydrogen atom, which would not be possible without aberration correction because of the contrast and the stability, the resolution. So the spherical aberration dominates significantly, and they just make these low Z elements, which are very small, and they have very low electron scattering cross section. So these aberrations just make these low Z elements invisible. So that's why you need aberration correction. So that's very important. So, but still, there are a lot of things that we have to correct. So basically, the modulation transfer function of your CCD detector. So this is readout noise, basically. It depends on the charge transfer, and it's proportional to the temperature. So basically, you can mitigate this readout noise by cooling your detector at sufficiently low or cryogenic temperatures. And there's electron loss in the microscope because you cannot have 100% controlled electron beam. So I'm not going to talk into detail about this concept. Then you have Johnson quantum noise. This concept is very important. So here, electrons are passing through metal tubes. So electrons are basically surrounded with metals. And metals have electrons. They have mobile electrons. And from Maxwell's equations, if you have the rotating currents, then you have magnetic field. So these nanomagnetic fields, they just deviate those electrons in the beam through their path. And for example, you have 10 centimeter metal tube, and you have velocity of electron of 230,000 kilometer per second, then it takes 500 picoseconds to pass through that 10 centimeter long tube. And while doing so, the electrons from the beam, they just see the snapshots of those magnetic fields. So you don't have sufficiently long tube to average this deflection or this distortion in the beam path. So this quantum noise is very difficult to correct for. And then you have dynamical electron diffraction. So if you have thick sample, basically thicker than 3 nanometers, then you have multiple scattering of electrons resulting in dynamic electron diffraction. And they can just introduce some artifacts in your TM image. And then you have tilt angle correction. So if your sample is tilted with respect to beam by even 1 milliradians, then you have error in your image of 1 picometer. So your image is distorted or it's not correct. So your image is having error. It's not correct image. So what you are seeing. So and for 1 milliradian of deflect of tilt angle, you have 1 picometer of corruption in the result. And again, you have residual lens aberrations, like you have electrical instabilities. Again, you have the shape of your aberration correctors or the lenses. They cannot be precisely very well manufactured. And then at the end, you have human interpretation. So you should be able to interpret those images correctly, because unlike light microscope, you're just seeing the shadow image of your sample. Whatever you have bacteria or amoeba, whatever you have. Basically, what you're seeing is the shadow image of your sample. But in electron microscopy, it's not shadow image. So because the electrons are scattering through the atomic columns, and atoms they are in the world of quantum physics. So you have to solve the Schrodinger wave equation to interpret those results, and computers do that for us. So basically, you're seeing these block waves or block states associated with your material on the detector plane. So basically, you are seeing a wave function, which is complex wave function. And that's what you are seeing, unlike the light microscope. And then I'll just, I'd like to show you, this is the environmental TM at Arizona State University. And this particular TM is an image corrected TM, and it is equipped with this set core TM corrector. And as we know that because of this reciprocity theorem, if you make this corrector upside down, it will become the corrector for STEM. Then it will become the probe corrector. But instead putting it right here, you just put it for the objective lens pre-field. So you put it above the objective lens in order to correct for the probe aberrations. And this component here, you can see it's the corrector component for this Titan microscope. And this is the optimized quadrupole octopole corrector for neon, developed by Krivanek and group. And here you have most recent aberration corrector. So this is a Neo ARM 200 CF. So this one is equipped with cold field emission gun, and you have ASCORE corrector, probe corrector. So this is equipped with the probe corrector. So it's advanced corrector for scanning transmission electron microscope. And this is also using the hexapole pieces, but with slight modifications in the optics. And you end up with getting the resolution of 0.05 nanometers or 0.5 angstroms. This is the information limit. So we have three definitions of the resolution. We have structure image resolution, which is Scherzer resolution, where you map at the first zero of the transfer function. Then you have lattice fringe resolution, which is twice as that of the Scherzer resolution. And then you have information limit. So beyond that, you cannot resolve anything. So basically, you have a Young's fringe experiment to see the information limit, but it's not very good to measure the information limit. So people have suggested some more approaches like tilt series beam or Zemlin tableau, etc. And for STEM, basically use Ronchi-grams to see the information, to see the aberration, the area which is aberration free, and you can know like what angle you can make, what convergence angle you can go up to without any significant compromise in the resolution. Because as I showed here, you need to work at high collection or probe convergence angle, because you have one way to reduce these aberrations by putting an aperture here. So you have small angle scattered rays here, but you lose this high angle information. And if you're familiar with the Bragg's law, n lambda equal to 2d sine theta or 2d theta. So theta is inversely proportional to d spacing. So at higher angle, you have the finer sample details. So you have to work at higher convergence or collection angles. And that's why you have to correct the aberration to increase the limit up to which you can extend your collection or convergence angle. And here is the very modern instrument, which is JOL ARM, Grand ARM. So it operates at 300 kilo electron volts, and it is also equipped with cold field emission gun, and it has the aberration corrector developed by JOL itself. So here we are using the dodecapole magnets. The working principle is same as of those hexapoles, but you have, this is called as expanding trajectory aberration corrector. So here you have short dodecapole, here you have long dodecapole, and the excitation of these two decapoles is a bit different in order to correct for twofold or fourfold aberrations. And this transfer lens, this transfer round lens, it corrects for the rotation, because your image in the TM is often rotated, because the path, if you know the path of the electrons in the lens, they take helical path. So your image is often rotated. So you have to correct for that image too. And at the end, I'd like to acknowledge my professors. So his Professor Peter Crozier. So he's the one because of whom I decided to make my career into transmission electron microscopy. And Professor David Smith also enhanced my knowledge in advanced electron microscopic techniques like aberration correction, electron holography, convergent beam, electron diffraction. And Professor Yang Jia, who taught me the kinetics and thermodynamics of solid materials, so I can understand the phase transformation and related phenomena in solids. And Professor Vivek, because of whom I got significant interest in catalysis, and I got significant knowledge of catalysis, because I'm also interested in investigating the dynamic nanoscale and atomic scale processes at the nanoscale by using aberration-corrected TM. So with this, I'd like to end my talk, and I'd like to say thanks to all of you who attended the talk, and I'll be happy to take any questions. So I can see here one question: what is the difference between image corrector and probe corrector? Okay, so in the image corrector, let me go back to the slides. So here you have image. So in the image corrector, so image corrector is used for parallel beam TM, which is CTEM. And because you're interested in post field of the objective lens, because you're using immersion lenses in TM, and your sample actually sits between those two pole pieces, which are pre-field, objective pre-field, and objective post-field. So your sample is just in between them. And if you're operating at CTEM mode, then you're interested in the post field, because it's the image forming lens. It forms the image at the image plane. So you have to correct the spherical aberrations of this post field lens. And if you're working in STEM mode, your pre-field is important, because it forms the probe, and the shape of the probe. What is the electron probe? So it's just the demagnified image of the electron source on your sample. So if it is distorted, or if you have a triangular electron beam, electron spot, then you're going to get artifacts in your image. So you're correcting the aberrations of the pre-field, then you're performing the probe correction. And if you're correcting the aberrations of the post field, then you're correcting for the image, or you're just doing the image correction. I'm not working in the biological field, so I don't have any experience with biological field actually. So I got this little aberration. So here one more question. I am new in this field. From the lecture, what I got is that little aberration should be still there to get lossy elements detection. Am I right? If yes, can't we have any solution to it? You can correct the aberrations. Like you have, basically you cannot correct all the aberrations because you have infinite set of aberrations. Like as I said in this equation here, you don't have only these two terms here. You have C5, you have C7, C9, C11, and so on. You have coma, you have star aberrations, and then you have astigmatism, you have chromatic aberrations. So you can never get fully corrected. And if you correct these two, but then you won't see anything. For getting phase contrast, you have to have some aberrations there. If you are imaging at exact defocus, for example, here. So if you're imaging with this condition here, then you're not going to see any contrast. So as I showed you in the small video, at the end, you arrive at the exact focus and you just lose contrast. So you need those aberrations. And as I said, there are infinite number of aberrations, but you still have limitations based on the physics. You have thermal diffuse scattering, you have phononic vibrations, then you have atomic scattering factors, and all these components contribute to the aberrations. And you have some aberrations called parasitic aberrations that which are very difficult to control. Ideally you should have no temperature gradient between the column and in the room, and you should have no flowing winds, you should have no electromagnetic fields, you should not speak. And in principle, if the resolution or the information limit of your instrument is say 0.8 angstroms, then the external aberrations or the parasitic aberrations should be less than 3 times. That is, they should be less than 0.3 angstroms. If you have more aberrations in the environment, then there is no use of correcting for the aberrations, and you just lose atomic resolution anyway. So you are just going to waste the money. And for the low-Z contrast is basically you have in positive CS condition, you have dark phase contrast and bright amplitude contrast, which is resulting from the electrons which pass through the tunnels between the atomic columns. And the dark phase contrast is basically when the electrons pass through the atomic columns. So they just both cancel each other out, and you end up with getting reduced contrast. So in NCSI, you have both bright phase contrast and amplitude contrast. And in that way, you enhance your contrast and you are able to observe the light elements, low-Z elements. Okay, any more questions? Okay, Wazir, so I don't think anyone has any questions. So you can take over.
I thank you, Shantanu, for nice talk. So I think hopefully everybody had something to learn new. And I did,
thank you.
But we did run into some technical problems due to the limited on time from the Zoom.
Yeah.
So I think.
So I just one more. I'll type my email address so that you can hold that. And if you have any questions, you just feel free to email me, drop me an email.
Because this meeting is also ending in 3 minutes.
Okay. Yeah. Sure. Okay. Thank you very much for your patience. I hope that I haven't bored you too much. And
yeah.
So
So I had one question, last question. So where this is going, the TEM, aberration correction transmission electron microscopy, where is this going? I mean, what is the future?
There's future, but there's still some limit to that. Like you have, as I said, you have phonons, you have some intrinsic factors that you cannot resist. Like you have phononic vibrations, and if you have vibrations, your atoms are just moving, they're vibrating. So you also compromise the resolution there, because like, for example, just imagine you're taking a snapshot of a person running, how you see that in the photograph. So if you take a snapshot of a moving object, then how you would see that? Yeah. So you don't have, and this cannot be completely removed unless you reach to absolute zero, which is impossible. Also, you have readout noise, but that can be overcome by using direct electron detectors. So there you have detective quantum efficiencies of 0.9, that is 90%. And that can eliminate the readout noise problem from the detection system. You cannot overcome the Johnson quantum noise. You cannot sit quietly. You cannot stop your heart from pulsing. So all these are ultimately going to add up to the aberration. So you should have well insulated instrument, and so best way is to operate it remotely. You're sitting into another room and just operating the instrument remotely. That's what the operation of neon or other grand ARM, these are often done.
So thank you for providing insightful information on aberration correction on TEMs. So I guess I will thank everybody, and we will end the meeting here.
Yeah. Thank you very much.
Thank you very much.
I'll just wait till the end.
Yeah, but I think it will end in 1 minute.
Yes,
so...
doesn't matter.
Yeah.
You can stop the recording.